or power stations. I'm going to show you how they work, why they make this noise, and also how to calculate them in this video, which is sponsored by Skillshare. The first 1,000 people to click the link and join will get a 1-month free trial. More about that later. Transformers look something like this. We find them illustrated with symbols like these in electrical drawings. Transformers are simply a device used to transfer electrical energy. It can change the voltage and current in the process, which is very useful. However, they only work with alternating current. They do not work with direct current. Most appliances are rated in watts or kilowatts, but transformers are rated with the units VA for volt amps or even kilovolt amps. We will learn why later on in this video. We can find small transformers used on doorbells or laptop chargers. We have larger versions to supply our homes and businesses, and we also find enormous ones which supply entire regions of towns and even cities. So where have you seen transformers used? Let me know in the comment section down below. There are lots of different ways to construct a transformer. I have some small common examples here, but they are essentially just the same thing. They have two separated coils of wire wrapped around an iron core. The generator or supply is connected to one coil, known as the primary side, and then the load, which is the thing we need to provide power to, is connected to the other coil, and this is known as the secondary side. If I take this one apart, we can see there are simply two separate coils of wire and lots of sheets of iron. That's it. The transformer is just transferring power between the coils. Electricity is dangerous, so do not try this at home unless you are qualified and competent. However, you can use Skillshare from home, and like me, you can follow Marques Brown's guide. This reduces the voltage, but increases the current. Now, this isn't a magical device that produces more energy than it receives. For example, a step-down transformer might receive 240 volts, and it outputs 120 volts. We see that the voltage halves, but the current doubles. If we multiply the voltage and current, we see the same value on each side. This is the volt amp value, which is power, or apparent power. And that has to remain the same. So if the voltage changes, then the current has to change in proportion to maintain the power. So why do transformers use the units of kVA instead of kilowatts? Well, the transformer is just transferring power between the coils. So we use the volt amp unit. The kilowatts depend on what you connect to the transformer. The manufacturer doesn't know what you will connect to the transformer. So they state the total rated apparent power in volt amps. And that's because in AC circuits, the load depends on the true power in kilowatts and the power factor, which is basically efficiency. And this varies depending on the device. Some energy is consumed, but it produces no work. It is just wasted as heat, and we call this reactive power with the units VAR. Power factor is just the ratio of true power and apparent power. If you think of a glass of beer, the liquid beer is the useful stuff. This is your true power in kilowatts. But there is always some foam which is useless. We don't want that. This is the reactive power, or the volt amp reactive. You pay for the total volume of the glass, regardless of how much foam and beer is inside. This is your apparent power in volt amps. Now, if you have a good bartender, you will get a little foam and lots of beer for your money. But if you have a bad bartender, then you're going to get lots of foam and not so much beer for your money. The transformer manufacturer is basically saying this transformer can handle a glass this big, but it's up to you how much beer and foam you put into that. The less foam you try to pass